Hello everybody, this is Rudra Pradhan here. Welcome to Engineering Econometrics. Today we will continue with the time series modeling, and the coverage is volatility modeling again. And in the last couple of lectures we have discussed various types of time series modeling, starting with the autoregressive model, moving average models, ARIMA, autoregressive integrated moving average model, and again taking the clue from ARIMA, we have discussed the arch cluster and GARCH clusters. In fact, in the last lecture we specifically highlighted the arch modeling, that is the autoregressive conditional heteroscedasticity model, and the structure of this particular arch model is that we like to connect error variance with square of the error terms. That is what the simple structure of this particular arch modeling, and the error is derived from a particular engineering variable or from a group of variables, where as usual we have a dependent variable, that is what called as let us say yt, and if it is only one variable that need to be predicted through this arch modeling, then we have to create a log variable corresponding to yt. The log variable will be yt minus 1, and then we just regress yt upon yt minus 1 and get the error term. That is the entry point to heteroscedasticity and the kind of arch modeling. Now, over the time we will have estimated model by integrating yt and yt minus 1, where yt is a particular engineering variable. Let us say rod transport coverage, that means technically rod length over the time or rod penetration over the time, and that need to be predicted, forecasted as per the particular engineering requirement or the economic requirement. On the other side, we will take this rod penetration is a variable, and corresponding to rod penetration we can have a set of other variables, independent variables, like rod investment, the kind of investment in other sectors. So, this may affect the rod penetration technically. So, now whether to predict rod penetration with log of the rod penetration, or we like to predict the rod penetration through rod investment and investment to other transportation sector, like port investment, airport investment, railway investment, and so on, with the assumption that the other investment may affect the rod penetration. Obviously, for a particular economy, the investment amount of investment is a limited component. If more and more investment will go to port sector or airport sector or railway sector, by default the less investment will happen in the road sector. Again in the road sectors, so the means the transportation sectors, and again in the road sector the impact will come, and that too for the rod penetration, because it will go to less money for the investment purpose, and as a result the penetration rate will get affected. So, that is what the problem background, and keeping this type of problems, we can predict particularly the rod penetration with lag of the rod penetrations, or rod penetration with lag of the rod investment and lag of the investment towards other sectors like port sector, airport sector and so on. In any case, we have two different structure. In the first instance, we like to connect y t upon y t minus 1, where rod transportation or rod penetration will be connected to lag of the rod penetration, that is y t versus y t minus 1. That is the first structure, first setup, and the other setup may be where rod penetration may be connected to rod penetration, that means lag of the rod penetration and lag of the investment towards the rod transportations, then investment towards the other transportation like port sector and airport sector. And by the way, both the cases we have a simple model and we have a multivariate model, and ultimately we need to estimate and have the error term, whether the error term is derived from the particular variable or the set of variables, depending upon the problem structure and the kind of requirement and the kind of prediction structure. In any case, in the first instance we need to have error component, that is what called as UT, and with the help of UT you can create series of lag UT starting with UT minus 1, UT minus 2 and so on, and then again we can start with the square of the lag error terms, that means technically u square t minus 1, u square t minus 2 and so on, and again over the time we can have a variance of the error term and again variance of the error term with respect to their lags. That means technically sigma square ut, sigma square ut minus 1, sigma square ut minus 2 and so on. That is what the procedure all about. So, that means technically in the arch and GARCH clusters we have two step procedure altogether. The first step is the mean equation, that is what the ut connected to ut minus 1, sorry ut connect means yt connected to yt minus 1, or yt can be connected with yt minus 1 and xt minus 1 set of other independent variables, and that too corresponding to their lags. That is what the mean equation, and after having the mean equations you can have the error component and then error variance, that is the second step of the process. And in the third step we like to have arch clusters by connecting error variance, that is what the term called as a sigma square ut, which is a function of square of the error terms such as u square t minus 1, u square t minus 2 and so on, and then we will go again re-estimate the particular setup and the structure and try to check whether the particular parameters are statistically significant and the overall fitness will be okay as per the particular requirement. And for that we used to have chi-square test and corresponding to coefficient of determination. And I think we have already discussed about this setups in the kind of arch modeling. I am just bringing the background once again to enter into the GARCH modeling. In the GARCH modeling it has just extend versions, that means we will do one extension compared to arch modeling. In the arch modeling we are connecting sigma square u2, sigma square ut with square of the error term, that too with lag variables. Technically sigma square ut equal to u square t minus 1, u square t minus 2 and so on. That is what the kind of structure. That means technically we can have like this. Okay, so we can start here, and technically, so the arch model is the cluster of sigma square u t as a function of u square t minus j. This is what the simple structure, and then if you connect, then you start with alpha 0, alpha 1 u square t minus 1, alpha 2 u square t minus 2, and so on. Obviously, one of the first hand requirement is to fix the optimum log length, because the particular log can vary up to q, but which is actually unknown or the kind of infinite structure. So, you make it finite, so that the particular structure can be bounded. If not bounded, then it is very difficult to estimate. In any context you can bound it, then you go for estimation. The usual procedure is you start with 1 log, 2 log, 3 log, and so on, and every time have the estimated results and check the validity, that to fixing the optimum log length depending upon the AIC and SIC statistics. Once you have that, then you can proceed accordingly. That is what the usual structure of arch cluster. Now, taking the clue from arch clusters. So, now the GARCH model is like this, where the beginning will be sigma square u t is equal to u square t minus 1 and sigma square t minus 1. So, that means we are allowing the error variance, log of the error variance. Now, we have arch 1, arch 2, arch 3, and so on. In the case of GARCH, that is what called a generalized autoregressive conditional heteroscedasticity, which like ARIMA cluster, autoregressive moving average, which has two parts, yt and its log and ut its log. The air part is yt versus yt minus 1, yt minus 2, and so on, and moving average part is the ut minus 1, ut minus 2, and so on. So, we are clubbing and have a ARMA structure, and exactly GARCH is the similar kind of setup. Compared to ARMA, the first difference is in the GARCH case is it is a nonlinear model, and we need square of the error term and the error variance. That is what the requirement, and then in the second step you have to fix the log component. So, now in the arch case we start with arch 1, arch 2, arch 3, because every time square of the error term is the independent variable. Since it is only one variables and that one cluster, as a result you can say arch 1, arch 2, and arch 3, and so on. If it is arch 1, then the model will restrict to simply alpha 0 plus alpha 1 u square t minus 1. If it is actually arch 2, then it will extend again. So, alpha 0 alpha 1 u square t minus 1 plus alpha 2 u t minus 2 squares, and so on, and again it will continue, but we need to fix the optimum log length by setting q equal to 3 for something, or 2, even it can be also 1. If it is 1, then the model have two parameters only, alpha 0 alpha 1. If it is actually a 3, then 2 lakhs, then it will restrict to 3 parameters. Now, exactly same in the case of GARCH, and we call it actually GARCH 1 1. So, that means first one is related to the square of the error component, and the second one corresponding to log of the error variance. So, now when we call GARCH 1 1, then the model by default will restrict to this much. So, this is the arch part and this is the GARCH part. That is what the technical actually difference. So, that means once you have error variance, then you can create log of the error variance, and then you can connect. Of course, both are connected to mean equation. In the software, it is very easy to deal. For instance, if you go through eViews, then there is option first you will find two boxes, and the first box will give you the mean equation estimate, and in the second box it will give you the Arch model output and GARCH model output depending upon your particular requirement and the particular command which you like to apply. Now, what is happening here? It is a kind of autoregressive. That is why the structure is called as generalized autoregressive. See here, if sigma square t is like this, then sigma square t minus 1 can be like this. Okay. So, here see sigma square t, then followed by t minus 1, t minus 1. So, if it is start with t minus 1, by default it will be t minus 2 and t minus 2. If it is start with t minus 2, then it will connect to t minus 3 and t minus 3. So, t minus 3, this part is the error part and this part the error variance part. So, a square of the error term and error variance both will go parallelly, and which can predict the current volatility. So, now since it is a kind of an autoregressive scheme, then ultimately it will have a kind of extension. So, you put all these value. For instance, you start with actually let us say sigma square t and square of the error term with respect to first log, and sigma square t minus 1, that to first log variance, and then keeping other things remain constant. If sigma square t minus 1 will start varying like this, and again sigma square t minus t will vary like this, then by default first you can put sigma square t minus 2 here, and again sigma square t minus 1 will be put here, and then finally if you simplify, then the whole equation will come in this format. That is what the final simplification with respect to the first equation, where sigma square t equal to alpha 0 alpha 1 u square t minus 1 and beta sigma square t minus 1. Then instead of putting alpha 0 beta, which may be or which can be written as let us say delta delta component, and by default this part can be component come to this side. So, we call as delta 0, and then alpha 1 y square t minus 1, then alpha 1 beta can be called as mu 1 e square t minus 2, then similarly mu 2 e square t minus 2, and so on. So, we need some kind of simplification before you go for the estimation. So, it is not a big deal, because ultimately in the Excel sheet we must have the data of a square of the error term and square of error variance. Then you can create a log and then simply you can connect. So, after that you can have the estimated value. That is what the kind of structure. Now, taking the clue, if you actually further proceed, the model can extend like this. Okay. Finally, we have model like this. Okay. And again if you simplify, it will give you a cluster like this, where L represents for instance log L y t. If I start, then it will be simply y t minus 1s. So, instead of saying beta square actually y t, then that means it is a L square y t. So, it is a 2 log technically. So, as a result, the entire component can be transferred into this form. Okay. So, it has another kind of structures, where the alpha 0 is connected with this much of extra weights, and alpha 1 followed by e square t minus will connected with this much of weight, and so on. Then finally, if you extend, the whole model by default will be transferred into this format. That is what the generalized format of GARCH model. So, that means we have square of the error component one part and square of the error variance the other part. Now, you can start with GARCH 1 GARCH 2 GARCH 3 and so on. So, the procedure is start with the GARCH 1. So, 1 square of the error term and 1 error variance log, means that is with respect to log. Then if it is start with GARCH 2, so alpha 1 is square t minus 1, then alpha 2 is square t minus 2. Similarly, beta 1 sigma square t minus 1 plus beta 2 sigma square t minus 2. That is how the kind of an extension you can do. And then finally, you have to fix the particular setup or this particular structure depending upon the clue of optimum log length, that is derived through again AIC statistic, SIC statistic or final prediction error. That is what the kind of structure you have to follow, then you work out the particular issue. Okay. So, this is what the generalized order regressive scheme, and then the issue is actually the GARCH model and then the kind of arch model. So, what is the basic actually difference? So, that means if you say that arch is a simple one, then GARCH is a little bit complex, and that too if it is a bivariate structure, then this will be a multivariate structure. Now, the question is why is GARCH better than arch? Obviously, the issue is it is not a issue of actually overfitting or the question of underfitting. We may expect that there is a question of overfitting and underfitting, but what is exactly requirement is the exact fitting. What is that is the need of the particular process. But the advantage is that it is a multivariate scheme, and then we may have a more accuracy to predict the particular engineering variables, because of the endogeneity issue, and we are adding the kind of error variance to that particular system. And finally, there is a high chance it has less likely to be these non-negativity constraints. That is the advantage of GARCH modeling. So, now the unconditional variance under the GARCH specification is that variance of ut is equal to alpha 0 upon 1 minus alpha 1 plus beta. Now, we have three different possibilities, either alpha 1 plus beta less than 1, alpha 1 plus beta greater than 1, and alpha 1 plus beta equal to 1. However, if alpha 1 plus beta greater than 1, it is called as non-tertiarity invariance, and if alpha 1 plus beta exactly equal to 1, it is called as a integrated GARCH models. That is what the case here. Okay, that is what the case here. So, that means technically if this happens, that is alpha 1 plus beta greater than 1, then it is a issue of non-tertiarity. Non-tertiarity is just opposite of tertiarity, which we have already used in the case of ARMA model, where we call instead of ARMA we call ARIMA, autoregressive integrated moving average. So, the I stands for integrations and we call it order of integration. So, the variables behavior, that too with respect to tenority, which is actually good signal of a modeling. If not, it is called as non-tenority. That means, in the entire time series starting with ARIMA to VAR modeling, which we like to highlight in this particular course, every time we will be checking the tenority issue. In technical, this particular issue is called as a unity root problem. We like to know what is the order of integrations where the variable will reach tenority. The procedure is like that, we can start with the original data and check the tenority. If the variable reaches tenority at the original levels, then the order of integration by default will call 0. If not, we transfer the variable, that too will go for difference equation, and that too we start with first difference, second difference and so on. And in the first difference, if that variable will again turn into tenority, provided that is not tenority in the original form, then we call as tenority of the variables, and in that case the order of integration will be 1. So, likewise you can proceed and we like to test till you get the variable tenority, and we are always keen to know what is the level where the variable reaches tenority, and that particular level technically use as the indicator to use further setting the ARMA model, ARCH model, GARCH model, VAR model. That is the technical point through which you can proceed and do the needful. So, obviously, the issue is actually to check the tenority. We have a separate lecture after this GARCH clusters. We will discuss the VAR modeling, and in the VAR modeling we will specifically highlight this unity root problem, because it is one of the mandatory component in the VAR modeling, which we may some extent skip in the case of ARMA and the kind of GARCH, but technically you should not actually ignore that one. But if you could not actually check, then that may be not so much big deal, but in the case of VAR modeling it is a big deal, because that itself will give you two different specification, which we will discuss in details in the later stage. So, in this case, so we have two different options technically compared to the first case, where alpha 1 plus beta less than 1. The first one is the alpha 1 plus beta greater than 1, where we call as term non-tenority invariance, while the counterpart alpha 1 plus beta exactly equal to 1 is called as a integrated GARCH. However, for non-tenority invariance, the conditional variance forecast will not converge on their unconditional value as the origin increases. That is the kind of structure. Okay. So, taking the clue, so we have here the estimation process, that GARCH and ARCH and GARCH model. Compared to ARCH model, in the GARCH model case, since the model is no longer of the usual linear form, we cannot simply use OLS, that is what the big deal again, but we can use OLS in the case of like the case which we have did through autoregressive moving average and ARMA. Here some extent actually it is a nonlinear in character. So, what we used to do here, we deploy another similar technique which is called as MLE, maximum likelihood estimation, and the method works by finding the most likely values of the parameters given the actual data. More specifically, we form a log likelihood functions and then maximize it. Okay. So, the procedure is like this, where we have step by step process, particularly for arch cluster and GARCH cluster. And what we will do here, I will just highlight the step by step procedure, how to have the arch estimation and GARCH estimation, and then I will give you little bit extension to GARCH models, because GARCH basket itself has lots of variations. That means, technically we have a couple of different models under the GARCH clusters. So, let us see first how we can have the estimation in the case of arch cluster and GARCH cluster, and then we will go about the kind of different types of GARCH models, and sometimes they are very essential to highlight some of the engineering forecasting, and that too as per the requirement of some decision making process. With this we will stop here and we will continue in the next lecture. Thank you very much.